A lamina is made by removing a small disk of radius r from a bigger disk of radius to. This is the lamina. The thickness of the lamina is constant everywhere. So if I take any piece of the lamina, its mass is proportional to its area. Now here we are asked to find the ratio of the moment of inertia about an axis passing through point O and moment of inertia about an axis passing through point P. Now these two axes are perpendicular to the plane of the lamina. Now if we try and get the moment of inertia about the axis passing through point O first. Okay, so how do we go about getting the moment of inertia? Now if I consider the lamina, uh, if I use just the lamina to get the moment of inertia, then it is a little difficult because I'll have to find its center of mass and then use the parallel axis. So instead of that, the idea that is commonly used here is it is little imaginary, but it is a very helpful idea. What is really done here is if you take a small disk of radius, imagine that this disk has negative mass. It's an imaginary thought, but a very helpful one. So this small disk of radius r having negative mass is placed exactly over the same spot where we want to have a hole. Now the bigger disk has the entire mass and then its mass is considered positive. Now when you place this smaller disk over that spot where we are trying to have a hole, the idea is that the negative mass would destroy the positive mass and then we end up with a hole. So our lamina is thought to be made up of two objects. One, we have a bigger disk with positive mass and a small disk with negative mass. Okay. Now they both contribute to the moment of inertia. So wherever we are using the mass of the small disk, you just make sure that you are using that negative sign. Okay, so now let us proceed. For review purposes, I will mention the parallel axis theorem here. The moment of inertia about any axis is equal to, so P is a general point, is moment of inertia about an axis passing through center of mass plus mass multiplied by square of the distance between these two axes. Now these axes are parallel to one another. Okay. Now the moment of inertia about the axis passing through O, if I look at the contribution of the bigger disk, so it will be mr square by 2. So again, we need the masses. So what we can do here is, if I take the area of the small disk, area is pi r square. So I can say the magnitude of its mass is m. Because we are saying that it has this special negative mass, we would say that it is minus m. And the area of the bigger disk is pi into 2r square. So this is 4 pi r square. So its area is 4 times that of the smaller disk. So we can say its mass is 4m. Okay. Now the contribution coming from the bigger disk is 4m into radius square, which is 2r whole square by 2. Now, we don't have to use the parallel axis theorem for the bigger disk because the axis is in fact through its center of mass. So that is the contribution. Now, due to the smaller disk, now if the smaller disk were getting rotated about the axis passing through its center of mass here, then the contribution would have been minus m r square over 2. But it is not getting rotated about an axis through its center of mass. So we are using that md square here. So plus minus m, and the distance between the axis is r. So I have r square. So if I pull mr square out and then look at the numbers, so I have 4 into 4 by 2, so that is 8, and minus half, and this is minus 1. So this is 8, so 16 minus 1 minus 2, so that's 13 over 2 m r square. Okay. So now let us look at how to get the moment of inertia about an axis passing through point P. Now here, neither the bigger disk's center of mass is aligned with the nor that of the smaller disk. So we are forced to use the parallel axis theorem for both bigger and the smaller disk. So the moment of inertia about an axis passing through P will be, now if I look at the contribution coming from the bigger disk, if it were rotated about an axis passing through its center of mass, which is this point O, it would have been we'll have to use plus here. So I'll write 4m into 2r whole square over 2. Now I need to add that md square. Okay, so the mass is 4m. So if you look at the distance between the axis O and P, that's 2r. So I have 2r whole square. And then we will look at the contribution coming from the smaller disk. So if it were rotated about an axis passing through its center of mass, it would have been minus m r square by 2. Okay, so make sure that you are using minus m plus, now I need the distance between these two axes. So I think that is easy. So just apply Pythagoras theorem here. So this is r and 2r. So if I look at, let's say if I call this as O prime P is simply square root of r square plus 2r whole square. So this is simply root phi r, and then substitute that. So what do we have? So we have root 5. I need to, okay, we need mass first. So minus m into root 5 r whole square. Okay, so now again from each term we can pull mr square out. And then what do the numbers look like? I think in the first term you still have 8, and in the second term 16 minus half, then minus. So what do we get? So this mr square, and this is 24, that's 48, then 48 minus 11. So I think we get 37 by 2. Okay, now if you look at the moment of inertia about an axis passing through O, we have this factor 13 by 2, and mr square is anyway, mr square by 2 is common both the expression. So when we are getting the ratio, I think the ratio is about P and about O. So IP by IO, ignoring the common factors, I think this is simply 37 by 13. So that is, I think they are looking at a nearest integer. So the nearest integer is 3.